In this video, we discuss learning outcome number 5 for lesson 4.4. It's all about understanding the difference between permutations and combinations. We also want to understand combinations of items and the combination rule for counting those. So remember that both permutations and combinations are arrangements of items, and permutations deal with position. With permutations, positions make a difference. So here with permutations, order matters. So the example I always think of is the gold, the silver, and the bronze at the Olympics. If you are one of these three women, the order that you're selected certainly matters. It will matter to you whether you're selected for the gold or for the silver or the gold or for the bronze. And if we switched those medals up, it would be a different permutation. So that's one example. Now combinations are, you can think of combinations in terms of committees. So this is our mnemonic. We say permutations go with position, combinations go with committee, because if you have a committee, rearrangements of the same members result in exactly the same committee. So if we have these same 6 people over here, it doesn't matter the order that they were chosen. It's still the same group. If I chose Sally last or Sally first, if Sally and her 5 friends are in the same group, it's the same combination. Excuse me. So this is the combinations rule. So let's say you've got n different items available, but only r of them are selected, and they're selected without replacement, so you don't put them back in. Then the number of different combinations, that's where order doesn't matter, can be found using this formula. Notice that it looks very similar to the permutations formula. It's just modified a little bit. The permutations formula has the n factorial, that's the number of items available, divided by the n minus r factorial, but it doesn't have this extra r factorial. The extra r factorial occurs in the combinations formula only. Now you can use this formula, you can memorize it. You can use the formulas and tables sheet from Triola to look this up every time. You'll have to know when you take your exam over this material that combinations are associated with arrangements where order doesn't matter. And then you would just go look that up if you want to. But there is an intuitive reason, why this is true. So we are going to focus on that intuitive reason why it's true and justify it. But if you're not comfortable with that, you can always just look at your sheet and that can help you. So you don't have to worry about all of the ideas behind it if those ideas confuse you. But if those ideas help you to remember this formula, that's even better. So you've got both options there. We're going to talk about the intuitive approach and the formulaic approach and show that you get exactly the same thing. This is just a modification of that permutations rule with that r factorial in the denominator. That's how it's been modified. Okay, so let's look at an example. It says in California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 through 39, and the same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in any order, so order does not make a difference. So the Fantasy 5, you just pick a number between 1 and 39. You pick 5 of them. The order doesn't matter, and you're probably watching it on TV, or at least that's how they used to do it in the 90s. I don't really watch TV anymore, but there used to be a time when they would show the Fantasy 5 drawing for the lottery in Florida, and you'd watch it on TV, and then they would be pulling like a ball out of a container, and they would tell you what that first number was, and that second number was, and that third number was. Well, the order doesn't matter. You'd be looking at your Fantasy 5 selections and saying, are those the numbers on my list? If all 5 of your numbers are the same as all 5 of their numbers, you win the Fantasy 5. But the order doesn't matter. So since the order doesn't matter, this is a combination. In part A, it asks how many different lottery tickets are possible if buying a lottery ticket means choosing 5 numbers. And then in part B, it asks, find the probability of winning the jackpot when only 1 ticket is purchased. So let's do this on paper. Let's do it intuitively, and then we will look at the formula and show that the formula gives us exactly the same thing. Okay, so we're here now. We're looking at the Fantasy 5. We've got numbers between 1 and 39, and you're choosing 5 of them. Well, if you're just counting intuitively, you'd say to yourself, how many options do I have for that first position? Well, I've got 39 numbers, so there are 39 that I can choose there. For the next position, I already used one of them, so I've got 38 possibilities left. The next position, I've got 37 possibilities left. The next one, 36 possibilities left. And for the next one, it's going to be 35 possibilities left. Now, if the order mattered, this would be the number of arrangements of 5 numbers that we could get from 1 through 39 if the order mattered. It would just be 39 times 38 times 37 times 36 times 35. That would be our count if order mattered. But let's say, and we're looking at this differently now, these are the possibilities. Here I'm actually thinking of numbers between 1 and 39. Let's say you chose 1 and 12 and 17 and 19 and 21. And you're listening. You're watching this on TV, if that's still how it works. And you see, okay, 21 comes up and 17 comes up. And you're getting excited, and 1 comes up, and you're getting really excited, and 19 comes up. And finally 12 comes up, and you win. Your numbers are the same as these numbers. Now your numbers are listed differently from the winning numbers, but they are the exact same combination, because in combinations, orders don't matter. The question becomes, well, if order doesn't matter here, when I do this, I'm actually counting this as separate from this. And I don't want to count this as separate from this. So I need to think about the possible ways that I could arrange 1, 12, 17, 19, and 21. So that I would get all the possible versions of this that would all be considered equivalent. They would all be the same combination. Well, if these are my 5 numbers, now let's look at it a little differently. I'm talking about possibilities again. Not actual numbers in the drawing, not actual numbers between 1 and 39. How many, if these are the 5 winning numbers, how many ways can I choose that first winning number? Well, I've got 5 possible numbers that could be that winning number. And then you'd have 4 left for the second position. And if you've already chosen those, you have 3 left for the next one, and then 2, and then whatever's left, that's the number that goes there. So there are actually 5 times 4 times 3 times 2 ways, that's 5 factorial ways of arranging these guys, but all of those count as the exact same combination. And we've counted them as different here when we did this. So to get rid of that counting some of those combinations 120 times when we only intended to count them once, we need to divide by 5 factorial. So let's see what we get. We get 39 times 38 times 37 times 36 times 35. And dividing by 5 factorial, that's 5 times 4 times 3 times 2 times 1, which gives us this 57, 57, 57. It's kind of a fun number. 575,757. That's how many possibilities or how many possible lottery tickets are actually out there. That's the intuitive approach. Now, if you're saying to yourself, I'd really rather just use the formula, I want to show you that the formula will give you exactly the same thing. If you have 39 possibilities and you're choosing 5 of them and you don't care about the order, so you're talking about combinations as opposed to permutations, according to the formula, you do this. So you have, this is our N, that's our R, 39 factorial in the numerator, and then you're dividing by 39 minus 5 right here, and then you're multiplying by 5 factorial. Well, if I expand this, that's 39 times 38 times 37 times 36 times 35 times 34 all the way down to 1. So I'll just call that 34 factorial. And 39 minus 5 factorial is 34 factorial. And you're multiplying by 5 factorial. So this part is actually the permutation. And the 39 factorials cancel, and you're just left with this right here, because you had 39 options for the first position, 38 for the second, 37 for the third, 36, and then 35. That's what the permutation tells us. We have this many possibilities. But with combinations, we accidentally counted these guys and all the other versions of these 120 times, and we didn't want to count them 120 times. Since we overcounted, we're just going to divide by that 5 factorial. And dividing by 5 factorial gets us here to 575,757, which is exactly what that formula tells us. So let's go back to the PowerPoint now. Okay. So it says how many different lottery tickets are possible? And we just found it using an intuitive approach, but let's use the formulas now. Because order doesn't matter, we use combinations. N is 39, R is 5. We do this and we get that number, that many possible arrangements, given that order doesn't matter when we're doing our counting. Now the second question, let's go back to it. It says, find the probability of winning the jackpot when one ticket is purchased. Well, if all of those possibilities are equally likely, then the probability of winning is 1 in 575,757. So it's a very, very small probability. And then it just, there's an extra point on here made by the author of our textbook. I think it's a little bit rude, but you can understand why it's true, or not necessarily why it's true, but you can understand why people say it. They say typical lotteries rely on the fact that people rarely know the value of this probability and have no realistic sense for how small that probability is. 1 in 575,000 is pretty small. That's why they say that some people say that lottery is a tax on people who are bad at math. Just like, ooh, that's really harsh. But if you buy a ticket, you do have a chance. Now, what I would say to you is buying one ticket is a 1 in 575,757 chance. So you are pretty unlikely to win that lottery. But buying 2 tickets is definitely not a good idea, because 1 out of 575,000 and 2 out of 575,000, like those aren't that different from each other. Now, if you don't buy a ticket, you can't win. You won't have any chance at all if you don't buy a ticket. But if you buy 1 ticket, you have a very, very small chance. Buying 2 tickets, well, I guess it doubles your chances, but the chances are so small. It's really not that different. So I would suggest that if you do want to play the lottery, buy 1 ticket and 1 ticket only. So that is it for our discussion of combinations.